So the next talk is being given remotely. It's by Pauli Lane from the University of Jyväskylä in Finland. That is exactly how you say it. And it's called Exploration Zone in the Newton Crater, and it's given remotely. So Pauli, just tell me when next slide, and I will do as ordered.
Okay, thank you very much. First of all, I want to thank for this possibility to do remote presentation, and all the organizers with help with my technical problems. Okay, I'm from University of Jyväskylä in Finland, but I'm now in Budapest in Hungary, so there was obvious some technical problems coming. But anyway, let's get started. This is the first slide, the title slide. As I was narrowing down the possible landing site, one region interests me as an astrobiologist. This region is located between 60 and 80 degrees south, near 180 degrees west. It is heavily graded, and as orbiting spacecraft like Mars Odyssey has observed, it preserves signs of remnant crustal magnetism and some signs of ground ice. And as water is very primary market for astrobiology, it's also available for human Mars missions. Okay, this area has not so many possible landing sites, but one crater spotted my site, and it's called Newton Crater. It's a quite large crater, about 300 kilometers diameter, located in the highlands of Terra Sirenum, in the southern sphere of Mars. So it's kind of Noachian area that has preserved the earliest history of Mars. Okay, then we can go to second slide, exploration zone map. I draw this exploration zone in my abstract a little bit southern, but I move it to a little bit north to avoid the nearby crater. So in this presentation, the Mars landing site and surface field station is located approximately 40.5 south and 200.5 east. And I have not so many science and resource regions of interest. I have my primary interest is to emphasize this importance of this region. But nevertheless, there are some quite interesting details and Royce here. You can go to the third. View of the science, Royce, and the threshold values are quite good covered, but threshold value for atmospheric science needs some further research for the rocks that might have trapped atmospheric gases there. And there are two lines with question marks, which are, to my knowledge, in mind the presence of indigenous rocks tied to one plus province and outcrops with remnant magnetization. So these remain to be put in mind in future research. And we can go to slide number 4, resource, ROIs, Rubric. Similarly, the first water resource threshold value is in at least at the resource ROI number 1 fulfilled, and possibly fulfilled in other ROIs also. For civil engineering threshold, it has flat and stable terrain and possible sparse rock distribution. And as I've seen from some topographic maps, it's not too inclined, it's less than 10 degrees. For the food production, sorry, I was looking for the threshold values now. So for the metal / silicon resources, some potential for metal and silicon needs to be further research further for confirmation. I don't go every row here in detail, so you can ask later if you want to go for the detailed analysis for each row. But I would go to the slide number 5, which is the title for science ROIs, and directly to slide number 6, introducing science ROI number 1. This is a very interesting crater that has some visible gullies that have evidence of present aqueous processes. So it has potential for present habitability. The small image below the image of the ROI indicates the location within the exploration show. Then slide number 7, science ROI 2. This has also interesting marks of fast water channels or marks of flowing water, and it's evidence of past aqueous processes, and also mean potential for past habitability. So, slide number 8, science roy 3. This is an interesting bulge, which is probable sediment from aqueous processes flowing from the higher level of the crater wall, and possibly has a potential for past habitability. Slide number 9, science roy 4, is a series of 3 craters that, of which 2 are inside the exploration zone. Those are different age, and could reveal layers from different eras. Well, that means potential for interpreting relative ages. Slide number 10, title for resource roys, and directly to slide number 11, resource roy 3. This is, I have added this because it's located less than 3 kilometers from processing equipment site and accessible by automated systems. It's the lower part of the channel that has evidence for aqueous processes and has potential for ice or ice regolith mix, and has also possible for metal silicon resources. Slide number 12, resource roy 2. This is the same as the science roy 3, and for the resources, it's probably has potential ice or ice regolith mix and potential for metal silicon resources. Slide number 13, resource roy 1, which is also science roy 1. So there is there was this evidence for present aqueous processes. So yeah, this is very potential source for water or ice or ice regolith mix for substantial production. Slide number 14, Rubric's title directly. Slide number 15, highest priority exploration zone that needs for science potential. There were these Noachian Hesperian rocks that have likelihood of containing trapped atmospheric gases. That should be researched because it's the only threshold criteria for atmospheric science. And for research potential, metal silicon concentrations are very known, so it is also an area of exploration, future exploration. Then slide 16, backup slide, and directly to slide number 17, prioritization list of exploration zone data needs. Orbiter or rover data to be collected to assess the science potential of the exploration zone. I've listed here the need for more high-resolution imaging of exploration zone to assess all Roy's threshold criteria. And for resource potential, there is a need for more accurate gamma-ray spectroscopy to assess metal and silicon concentrations of resource Roy's. So this was not so much about the detailed analysis of the different Roy's, but emphasis for this region and this promising crater as a possible landing. That concludes my presentation. Thank you very much. Thanks for sticking with the topic.
And if you can stay on the phone after the next three talks, you may, so you are available to answer some questions during the discussion period. That would be great.
Okay, thank you.
Okay, our next speaker is Donna Viola, who's a graduate student at the University of Arizona. She's going to talk to us about two different sites. We've given her only a single time slot, so on your sheet there's two different rows. They're next to each other. It's two of those, right?
Yeah, Erebus Montes and National.
And Alfred and Colin are co-authors. So, Donna, go ahead.
All right. So good afternoon. Thank you all for coming back from lunch. So like Dave said, I'll be talking about actually two sites in this Arcadia Planitia area. And just to motivate this work, I'd like to start by quickly going through some of my dissertation research so far, looking into the shallow subsurface water ice within Arcadia Planitia. So the area that I'm talking about is basically this big red box here. And what I've been doing is looking at what we're calling expanded secondary craters, which you can see in this figure here. But they're basically, you have this central crater bowl and a shallow extension up to the surface. We think that these form by impacts into excess ice. So this thick, relatively pure layer of ice very close to the surface. When these impacts hit, the ice sublimates, so you kind of get the diameters will grow. To give you this unique morphology, we see lots of these in Arcadia Planitia. They tend to be found in clusters, and many of them can be radially linked back to at least 4 primary craters within this area. So this is just a quick map. So all these blue areas are clusters of expanded secondary craters. So they're found throughout this region. And in fact, since they're secondary craters, we can also say something about the age of this ice. So we can source them back to a few primary craters. We can say that this ice sheet has been there for tens of millions of years. So it's a stable resource. It's been there for a long time. It's very close to the surface. So I'm kind of going to try to target this area. There's also additional evidence for shallow subsurface water ice here today. So these maps are showing recent impact craters that we've actually observed in our repeat image data using CTX and HiRISE. So all the black dots in both of these maps are impact sites. The white dots, you can see at higher latitudes, are the ones that we've actually seen ice exposed. So you have an example of one of these craters where we actually see this white material that's exposed. We see it disappear over time at a rate that's consistent with ice sublimation. So it's very strong evidence that this ice sheet is throughout this area. In fact, you'll note, I'll do this. So the two sites that I'm talking about are denoted by these stars. And they're kind of in this area where we can see multiple locations of ice exposing recent impact craters. So we know that this ice sheet is there. Again, these are exposing excess ice, this relatively pure ice. It's probably almost entirely free of dust, on the order of greater than 99% water ice. So this is a great potential resource for human explorers. And Arcadia Planitia is one of the few regions in this area of Mars where this abundant shallow ice is present at relatively low latitudes. So the two sites that I'm talking about are pretty close to 40 degrees north. So again, it's within the 50-degree limit for this proposal. Something else that's useful to note is that We also tend to find these new impact craters in dusty terrains, which is a potential challenge that I'm going to address in a little while, but it's also possible that this dust is helping to protect this ice sheet and keep it stable for longer periods of time. So this may end up being a trade-off that we need to consider in sending human missions. So to take a look at the geologic context, this is the recent geologic map that Jim Skinner talked about yesterday. So there are a few different units within Arcadia Planitia in general. So there's this late Hesperian lowlands region. There are some Amazonian Hesperian volcanic terrains, Amazonian volcanic terrains, and late Amazonian volcanic terrains. So these are generally sort of some of the more recent geologic terrains that have been deposited on Mars. So in trying to figure out where to actually target sending a human mission, I was trying to look for locations where you may have access to some of the older parts of Mars. And sure enough, there are a couple of locations in the southern part of this Arcadia Planitia area where we have exposures of, in the case of Erebus Montes, Hesperian-Noachian transition terrain. And for Acheron Fossae, it's actually in late Noachian highlands. And so two different landing sites were born. So I'm going to try and get through as much of this as quickly as I can. But there are a few challenges to targeting a mission in Arcadia Planitia. I just wanted to put these out there kind of right up front. Like I've mentioned before, it is a fairly dusty region, which may be good for preserving the ice, may not be as great for trying to land a human mission there. So the specific landing locations that were chosen in each one of these exploration zones was attempting to minimize the dust based on this test dust cover index. So you can see these boxes in the middle and sort of the green and blue areas of this, a little bit less dusty, so it may be sort of trying to help provide a compromise to still be able to access these icy terrains. A related challenge is that there's very little chrism data, which isn't really surprising for a dusty region. It's related to the first one, because dust and chrism don't really get along. You don't really get a useful spectra, so there's not a whole lot of information here, which again is another challenge to exploring this site in depth. There's also not a whole lot of high-rise coverage. Disappointing because I'm at the University of Arizona working with high-rise, but so most of what I'll be talking about will be focusing on, there is full CTX coverage pretty much across both of these areas. So most of what I'll be doing from here on out will be looking at the CTX to sort of describe some of the features of interest in these areas. So getting into my first landing site, Acheron Fossae, so which was this point up here. So here is the map of the exploration zone. I have just a few science ROIs described since I have two of these to get through. But you have at the landing site and surface field station is right here in the middle, centered at 39.8 degrees north, 220 east, and it's at an elevation of minus 3,100 meters, so very well within the 2-kilometer limit of this. And then jumping right into some of these science ROIs. So first off, there is, in the southern part of the exploration zone, is the Acheron Fossae Graben system. So this, again, is the late Noachian highlands terrain. So this is a place where we can access some of the more ancient rocks on Mars. This unit can be found regionally and globally on Mars. And of course, this represents significant tectonic activity in the Martian past. So you can kind of see all of these Graben features throughout here, and there are many different features of interest within this larger region. I'm just going to highlight a few of them quickly, so we don't spend too long on it. But so here we have some possible channel-like features that you can see, at least at the CTX level. Towards the edge of this, there are a few other locations. So these may represent some potential past aqueous activity, maybe habitability potential. I don't know enough about how we're describing habitability potential, so I don't want to emphasize that too much. But so there are a few of these features throughout this ROI. There are also these exposures along the Graben walls at multiple locations. So this particular example is coming from right in here, but you can see some of these blocks jutting out from the slope of the Graben, which could represent some access to some of the older bedrock units. We also see glacial fill on the Graben floors. So I'll be talking a lot about Amazonian age ice throughout the rest of this talk. But so this most likely was deposited after the graben itself formed. But we can see glacial fill, these striations along the walls, flow-like morphologies throughout a lot of these graben structures. So we can get sort of at least some relative ages, looking at those, and access to this Amazonian subsurface ice, which is pretty much everywhere in the areas that I'm talking about. The second science ROI is at this very edge of the Acheron Fossae graben system, and it's another one of these small channel-like features. This one we actually have some high-rise coverage of. You can see the channel coming in along here. It doesn't appear to be in any kind of fluvial network, so it may not have been from open water flow, but it's possibly evidence of a subglacial liquid water flow. Still liquid water, still maybe potential for habitability, so still of interest. The third science region of interest that I identified is up in the northern part of the exploration zone, and it's these big blocky terrain, looks almost like a chaos terrain. To me, we also can see evidence for flow features along kind of in between these big blocks. So most likely more Amazonian glacial fill in this area. The fourth science region of interest is this double layer ejecta impact crater. It might be hard to see on this screen, but so for anyone who doesn't know, double layer ejecta craters are sort of controversial. We see them in areas with ice on Mars. We've only really seen them mostly on Mars. But we're not really clear on how they form. So being able to get a field geologist to go out there and look at this and figure out what's going on would help to settle some of the debate in the impact crater community. We also can see that this has concentric crater fill inside of it. So some of these glacier type textures. I think someone's already mentioned concentric crater fill, so I won't go into too much detail. But this again is another opportunity to access these Amazonian aged subsurface ice. And it's also access to a primary crater with a unique ejecta morphology, which I think is pretty interesting. So moving on to the resource ROIs. I've actually only identified sort of sample locations for this. Really, this ice is everywhere, and you can kind of pick anywhere you want and start digging, and you're going to get to ice pretty quickly. These particular locations, again, very close to the landing site habitation zone, are actually on the fringes of this lobate, most likely ice-rich ejecta material. But again, excess water ice is pretty much everywhere, so you can move these around sort of as you wish. I'm going to skip through the rubrics because I'm down to 5 minutes. But the key here really is that the access to water ice is incredibly valuable, and that's kind of the primary benefit of this site. So moving on to the second site, which is this Erebus Montes. Again, here's the map of the exploration zone itself, the central landing site, a couple of sample resource regions of interest, as well as a few science ROIs. So this is located at 39 north, 192 east, elevation of minus 4,000 meters. Again, still well within the requirements. And so actually, science regions 1, 2, and 5 include some of these exposures of the Hesperian-Noachian transition terrain that I mentioned earlier. And a lot of these also have lobate debris aprons around them, which fortunately Jim had told you all about earlier, so I don't have to go into detail on it. Let's take a quick look at one of these. So the first region, right up in this top area, is one of these Hesperian-Noachian transition zones. So potential access to some of these older rocks on Mars. We also see these ice-rich lobate debris aprons surrounding most of these peaks in here. We can also, so here's one of them, you can also see some evidence for these expanded craters that I mentioned earlier. So again, further evidence for ice in this area. This ROI is actually located very close to one of the ice exposing impacts as well. So we know it's definitely there, which I think is very valuable. The second science ROI, again, is very similar, Hesperian-Noachian transition terrain. This also includes this buried, degraded impact crater down in the corner. More evidence for lobate debris aprons, expanded craters, lots and lots of ice. Can't emphasize that enough with this talk. The third science region of interest is actually this southern area here. It seems like a contact between multiple episodes of Amazonian volcanism, so you can get some relative ages for that. There may be the possibility for lava tube caves in here. I haven't had a chance to look at that in detail, but as we heard, I think yesterday, caves could be valuable for habitability, for habitation, so there is some potential for that here. And these areas still, again, include some evidence for subsurface ice. So the fourth science region of interest is another barely buried crater. We can see some of these glacial features, like this outflow at the crater wall. More ice here, same story. And then region 5, again, is very similar to 1 and 2. For this is these low-bay debris aprons, Amazonian lava flows, glacial and periglacial activity. So the resources, again, these are just samples. I think that you could dig anywhere to get your water ice. I don't know enough about the metal resources to comment on it a whole lot. So I will leave it at that. So once again, we have, lots of ice. Yeah, so lots and lots of ice. And the resources, once again, lots of ice. And then I just kind of wanted to end on this, kind of this bonus science ROI is sort of how I thought of it. And that for both locations, the Arcadia Planitia ice sheet itself is not only good as a resource, it's also of scientific interest. So being able to access it for human use means that it should also be easy enough to sample and study. So it can address a lot of different science questions, and so some of these I have listed here. How did the ice sheet itself form? There are a few hypotheses, but not really consensus on that. Timescales of deposition, how long it's been there. My expanded secondary craters can tell us a little bit about the minimum age, but there's no constraint on the maximum age. How is this ice interacting with the atmosphere? Did it preserve organics or other biosignatures? So I think it was Joe Levy this morning who talked a little bit about how ice and these sorts of things can be related. And then could the ice have contained habitable microenvironments now or in the past? So I guess the point is water ice everywhere, but not all of it is to drink. It really is a valuable scientific resource as well. So high priority data needs, similar to what most people have had, higher resolution data, specifically composition. Again, the dust may affect these crystal observations, so a potential strategy is targeting them using other data sets, maybe tests, to find areas with slightly less dust to try and get these crystal observations. And of course, higher resolution of these near surface ice deposits. Is there any heterogeneity to it? Where are the best places to get to it? And these instruments have already been talked about, so I will leave it at that. Thank you for listening.
Thank you, Donna. Very nice. Okay, our next speaker is, according to my agenda, is Don Barker. There he is. Hi, Don. How you doing? And I'm not sure if you have co-authors. Yes. There's a couple. You can introduce them. At least one of which is Steve Clifford. And you can point out your site.
Sounds good. Good after lunch. My name's Don Barker, and I've got 3 cohorts with me on this. Dr. George James and Dr. Greg Shamatoff and Dr. Steve Clifford. I don't have a doctorate yet. I'm actually working on one in geology at UH, but I do have 4 master's degrees, so I kind of fill in the gap behind them. This image, and please take note of my abstract, my first selection of the landing site, EZ, was half the size of the required one. So the paper is at the paper's at 50. I've gone back and done the rest of the slides at 100. But actually, that did not change my premise for this, because my whole interest in this, as you see, this document here, has been for resources for the last 20 years. April '98 was when we first published this, out of a master's degree project, and we started with resources back then. So, a little bit on the site selection. We're just out of Arcadia, Planitia, and along the Flagradorcia region, 39 north. Same latitude Jim and the last talk and everybody else is talking about is the high latitude or mid latitude. Good places for ice. Oh, sorry. Make sure I don't. Back up here in the top right hand corner. I've selected basically, well, when it was at 50, and I'm going to do that all the time. When it was at 50, I didn't have any changes. What happened when I bumped to 100, this crater, 75 kilometer diameter crater up here, Tyndall, actually fell in it, so that became one of my science resources. Or the science resources, but all my resources are the same throughout this entire region, basically. So there was no change in that. So the first science resources are the dome structures, which are throughout this region, and there's a lot of work that's been done on that from some other authors. 2 is hydrated sulfate find from Omega. 3 is fluidized crater impacts all over the region, of course. 4 is Tyndall crater itself. Resource 1's water everywhere. We've already talked about that. Ice. 2, I kind of threw sheet silicates into that. I'll go into that more later. And 3 is the plains unit itself. All sorts of stuff that are at the top level that could be used as mining resources. Test dust index in this region, right through the center of this. Low dust, which is what we're looking for. Got in the top end there. And that's a test over Themis. The rock abundance, low, so that's good for the landing site and the landing capabilities of the vehicles, especially big 30 metric ton ones. This is a close-up with the CTX of just the site I selected, or the landing ellipse. This point here, notice I didn't put landing sites or basically the base structure itself, because the region, even through this entire region, it's very similar. So there's so much room that can be moved around. Move this entire EZ around here, and you're not changing very much. So we got an average elevation, 3966 low. Thermal inertia's medium. Nice flat area. Albedo's medium range, and the dust index is low. Average temperature of the region is about minus 73. And the good thing about the low altitude and stuff like that for landing, it helps. Oh, that's on another slide. I'll get there in a minute. Hey, here it is. Low altitude. Here's another close-up again of the region. So you're seeing even better areas for touching down the vehicles. For large EDL landing operations, the denser atmosphere basically helps that out. It also acts as a greater resource for mining. H2O and CO2 itself, Sabatier reactions and producing your methane, oxygen fuel supplies. And again, I said moderate thermal inertia and albedos. The rubrics basically did what everybody else did, filled it out as best as I could, and I'll let you guys hit those later. But we touch on most of them. I'm not a strong point in the biological side of it, so that still needs to be addressed a little bit. But there is potential, except for the temperature is kind of cold up there. Resources, that was my whole premise, so that's going to be filled out almost completely. Ken Tanaka's latest map. Most of this is Hesperian, Amazonian. Still trying to tie in the Noachian, but the crater might help, the big one. That still remains to be seen. So, Science ROI1, the entire region, basically. There's actually called the Tyndall Dome Field because you get these large structures out here that are, and 3 papers here that I really liked for these ones. Subaerial extruded domes, cryptodomes, intrusive ice magma interactions. Some people propose them as mud volcanoes. Of course, the ice-rich regolith, especially around the circumference of these features, because you got mass wasting and another potential source for storing or having sequestered water ice. You can study changes in obliquity variations, and I'll get to that in a second, and silica-rich rocks. And I didn't notice nobody else put that in there, but I know it was on the sheet. So again, let me see. There was a. I'll get back to that. Okay. And here's a high-rise blow-up of that. There is a little bit of chrism data in these areas, not a lot. So I didn't focus on it, but just wanted to highlight that some of that was there. Ice-rich textures everywhere, polygonally fractured grounds and brain terrain. So this is just part of the whole hypothesis of ice in these latitudes as a primary resource. Hydrated minerals. If you're going to go any place and land people, you want to use every single resource that you have available to you. You got water ice, you got hydrated minerals. You're going to go after both. At that point, it's an energy equation. And then you start looking at what's your energy sources for the base. So this was one of the omega dots that was right in the area. Mineralogy, sedimentology, geochemistry, weathering, all these processes are good science candidates for this feature. Number 3 was, Jim's talked about that, the last talk talked about that. These structures are all over the area. A lot of these in this area are a lot smaller, which might make them easier to characterize in a short amount of time. But then you've got one of the fluidized, and then you've got all of these dome structures, these possible volcanic features, and they're throughout this region. So again, the geoscience crosses all those regions. Close-up of the inside of that crater. I'm not going to speculate on those, but they look nice. But the other stuff you notice, all over ice surface interaction materials. So my primary resource is just about everywhere, so that's okay. Tyndall crater itself that I got to dump in there. You can see it's a very large crater, but it's been infilled quite a lot. So access to the crater, not the crater floor itself, but the infill of the crater would be very simple through these slopes, hoping some Noachian material might be out there, but I can't guarantee that. No geological map has covered that yet that I know of. High rise again of that. You can see how low and broad that crater rim is. Inside these smaller craters just outside, lots of ice interactions, and I was looking at the high rise again, and there's some other ones out there that have they look like pancake structures inside. It's amazing. Okay, and if I'm going too fast, please tell me. I know we're a little bit on a budget, but that's okay. So my whole purpose, as you saw on the first slide, to go to Mars is to mine ice. If you mine ice and you go for the thought process of permanence as opposed to our traditional space exploration mentality, it makes you start thinking about how you're going to do it a little bit different. So we've seen this plot many times. It's been around forever. That's a conservative number in this area, the greater than 4 weight percent. Marsis has given us some stuff on volumetric ice content and porosity. And there's actually some GCM models that have shown that this area is a dumping ground during high obliquity phases for ice and precipitation. So that was kind of a nice thing. Here's the Flagramontes, and some of these sites that have shown the recent impact ice are just above where we were, so it's nice and close, so that was comfortable. A little bit on the mining, and you've got all these materials that we want to use as resources, but we've only talked a little bit about the actual energy that we're going to be needing as a base. To me, there's 4 primary energy sources that we will need to do at Mars, and you don't do anything in human spaceflight with one thing. You always have a backup and a second backup and a third backup if possible. On Mars, we had one person mention the fact that we might have nuclear energy, hopefully certified by then. Solar's been around forever. Methane, oxygen, we're going to be producing it, hopefully internal combustion engines. We can use that. And the last one is actually wind-generated power, and we've done work on that. So 4 sources of energy, because if you're going to start actually getting to the point of actually mining and producing at that point, it takes a lot of energy to ramp up something to get 2,000 degrees. And aluminum is probably one of the worst things to get. And that's out of an ore that we mine here, and not the harder elements that we would have to take aluminum out of on Mars. I don't think we found any ore deposits on Mars yet. It'd be nice, but I don't think we found any yet. So all these melting points to get stuff up, to start separating out the elements that we want to use, energy intensive. The second resource ROI that I said, every resource ROI is a science ROI, but not every science ROI is an equivalent resource ROI. So this is, again, both, just like the water is. So there's some high indications through the center of this region that we got sheet silicates and a little bit of a chrism data on that. So it could be a potential resource. The Omega does kind of the same thing for dust, and it showed low dust with the ferric oxide nanoparticles. So it's low slopes, medium fine grained surfaces, easy for reclamation, civil engineering processes, moving dirt around, enhances mining manufacturing. There's been recent work done on 3D sintering and construction processes, and of course traverse operations. You want to make that as simple as possible, especially if you're going to move any large pieces of infrastructure or tools. Also, there's a whole section in some of the papers that I talked about earlier. This area has potential for lava tubes and tunnels, which we know can be used either as sources to put buildings in or hide from particle events, etc. So a whole bunch of interesting stuff there. And I just went and grabbed a whole bunch of the test data in this area. And what else can we use that would be mineralogically interesting? So there's some potential, but the problem is for most of the test stuff, you're down here in the detection limit bands. Up here, you're a little bit better. Here, you're a little bit okay. So again, the chrism and other types of instruments will be needed in the future. So the highest priority is a permanent and growing and sustainable, and I don't want to use the word field station. I don't want to use the word base. I want to go towards the word settlement, just personally. So neutron spectrometer, we talked about that. All the radars, we talked about that. Chrism and high-rise, I think everybody's had that. Can be helpful. Nobody's talked about any of the, this is the radiation environment experiment, characterizing for other human health factors. So other types of experiments that would go down that path would be needed. So primary driving site, driver in this entire thing is water. We go to live permanently. And I like to say that we go to do ice mining and water first before we even start selecting the quote-unquote science goals. Proven producible water, just like proven and producible oil. We want to get that first. 2 more slides. The easy concept I thought is very interesting if you consider this as a settlement, a township. I don't want to use the word base. Now, start adding these field stations where you could actually transfer from this point a radiation shelter, a small field station out to another point that has another easy around it. And once you start building these out, you start building up an infrastructure. Then you add in the robotic potential for pre-sorties or reconnaissance. You start getting regional upticks in capability. And I'm not going to go into this too much, but there's 3 more slides on a philosophical critique that I've gone, a tirade I went into, on, why Mars. We still have the problem of selling why Mars to the public. And then there's the problem of why Mars has always been 20 years from now. So I'll let you read that at your leisure. And a little selfless plug here on a paper I just published earlier this year, kind of trying to address this why question. And I'm going to cut it off there.
Galagus 2, the sequel.
Thank you. Okay, so again, let's see. My name is Zachary Gallegos, and my second site that I'm proposing is in the Proternillus Mince region, which you can see right here, just to the east of Deuternillus Mince. And again, I'd like to thank Horton Newsom. And I also like to mention, I forgot the first time, that I want to be a Mars explorer one day. I'm astronaut candidate for the Mars 1 mission. Take that with as many deposits of salt as you want to. Okay, so zooming in here, looking at some local features around the EZ, you have this large crater over here, Moreau crater, and then down here you can just see the very edge in this view of Rideau crater. And I've picked out a landing site right here, which is inside a crater, calling it LZ crater for now, and the habitation zone just outside of that. And for broad geologic context, we have mid-Noachian highlands, the early Hesperian transition, Hesperian-Noachian transition, Amazonian-Hesperian impact, and Amazonian-Noachian apron unit. And also the remnant magnetization in this area, a little bit of a negative anomaly here, so you can maybe access some of these deposits in here, and it looks like it's just mainly the Noachian stuff. Okay, and looking at the ROIs, my ROI number 1 is the Amazonian Noachian apron unit. The ROI number 2 are these outflow channels that are coming out of the Noachian highlands. ROI 3 is the ejecta and the inside of Moreau crater itself. ROI 4 is the Noachian highlands. ROI 5, the Hesperian transition, and just a little sliver of ROI 6, the Hesperian-Noachian transition. And I should mention that not all of these are resources. The resource ones are in the blue, although you can find some good resources over here in the water resources, rather. The water resources are in blue. You can find a little bit in Moreau crater also. So science ROIs. You have the Amazonian Noachian apron unit. It's all this fretted terrain out here. And you have lots of ice and Noachian bedrock. So you can sample that. So we have potential past habitability, potential present habitability, low, but still potential. Noachian, Hesperian trapped gases. Range of datable surfaces, igneous rocks, and lots of other stuff. Okay, ROI number 2, outflow channels. You have these 2 big outflow channels coming from here and here, flowing into the EZ, and the EZ extends about right here. So you can drive up these outflow channels and sample all the way up, sampling the fill inside and also the Noachian strata. And the rubric for that one also, potential habitability, trapped gases, igneous rocks perhaps. Moreau crater is science ROI number 3. You have impact deposits, datable surfaces, trapped gases within the impact deposits, and water ice also. And the rubric for that also, a lot of these rubrics look pretty much the same. So I'll breeze through those. So ROI number 4 for the science is the Noachian highlands. You have igneous rocks, datable surfaces, trapped gases perhaps. And like I said, the EZ extends about in this range right in here. So you have plenty of Noachian area up here. And this one, I'm not saying past habitability. There's not much water ice. There could be, just in the permafrost. But and early Hesperian transition unit, you have igneous rocks, datable surfaces, potentially trapped gases. And so not much habitability, maybe, as you have outflow from these channels. But I'm not saying any green in there. Outcrops with remnant magnetization, I'm saying maybe on that one because it looks like the extent of that stops where the Noachian stops, and so that might be a little too degraded, but you never know. And the Hesperian Noachian transition unit, like I said, we only get a little sliver. The EZ extends about right here, so you barely get any, but it's a chance to sample it and see if it's the same stuff, see if it's different. So you got igneous rocks, possibly datable surfaces, trapped gases. And that one looks a lot like the rubric for the last one. Breeze through that one again. Okay, and so here's the science rubric. You got potential habitability, past and present. In the first three ROIs, that's the Noachian apron unit, Amazonian Noachian apron unit, these outflow channels, and in Moreau crater. And trapped gases possibly everywhere here, either in the impacts or in the actual rocks themselves. And range of datable surfaces all the way from Noachian to the Amazonian. Igneous rock from different time periods. Glacial ice, lots of glacial ice, I should say, actually. And moving on to the resource ROIs, you have the, again, Amazonian Noachian apron unit, lots of water ice. And I'll show some close-up images of that in a minute. And so, potential for ice, and they all fall within the latitude and elevation restrictions. And let's see, I didn't want to go for cobbles in this, though you could probably find cobbles and other civil engineering sources in the till of the glaciers. So the outflow channels, there's lots of lineated valley fill in here, some glacial tongues coming down off these little tributaries, and also some hydrated mineral potential. And here's one of them, and the other one here actually branches off in a few areas. So potential for hydrated minerals, ice. And Moreau crater, you have impact glasses, which could be used for silicon, if you can manage to get that out, and water ice also in the center. And I think you can get through into the crater through this little outflow channel right here. So it's possible you can explore this little area. And again, potential for water ice. Also, potential for metal silicon, because you have this big impact crater here. Could provide a small hydrothermal system, maybe concentrate some of the elements in there. And the Noachian Highlands, could probably use that for cobbles, regolith, other sorts of building materials. And you can access that either in the outcrop form or washing down through these outflow channels. And like I said, just focusing on that for the Noachian Highlands units, just the civil engineering aspects. And again, the early transition Hesperian unit, just cobbles, rocks, regolith. Probably you could find a bit of ice in there too, but that's not what I'm focusing on for that one, because we have such, large expansive ice in the Amazonian Noachian apron unit. Okay, probably I should take that out. Okay, moving on. So the resource rubric, lots of water ice, potential for some silica and other metals, other resources, cobbles, probably cobbles everywhere along the glacials. And just as an overall for the science and for the resources, you have potential habitability, trapped gases, range of meteorological diversity, lots of datable surfaces, igneous units, and also the impact units too. And up here, the hydrated minerals, ice, and I haven't exactly narrowed down where we would put the processing units, so those are mostly open circles because you can set them next to any of these glaciers or any of these deposits and have them within 3 kilometers. And keep going. Okay, here is the high-rise Chrism currently. So more than my last site, which is good. You have Chrism over here and Chrism over here, mainly focusing on the Amazonian and Noachian apron unit. And you also have some down here in the valley fill, and lots of high-rise everywhere, looking at the glacials again, and also in these valleys. So here is one of those glacial tongues coming out of one of those mesas, and looks like a glacier to me. And looking, I don't think that's the same one, but just another one of these mesas. You can see the bound water looks like a lot of water. And here is here's a high-rise image of, here's the landing site crater, and here is the outflow channel going from the crater that you might be able to follow and get to the rest of it. Not might, you could probably follow this and get out, hopefully. And inside Moreau crater, you have lots of cool stuff to look at, possibly a lot of ice, impact deposits, and yes, bound water. You can get some water out of there if you really need it. And in the highland outflow channels, you can also see these glacial deposits coming off the side of the Noachian Highlands units, possible for use and resource. And for data needs, I'm saying that for science, we need high-resolution imagery and spectroscopy. And an MSL class rover or better would be good for science reconnaissance, going to the glaciers, going to the Noachian Highlands, and some of the impact craters around. For resource needs, you need a rover again to look at the ice, make sure it's feasible to mine it, impact glass, metals, potentially. And orbital data, we need high-resolution imagery, spectroscopy, and possibly more radar data, just to confirm those, even though they look pretty convincing as glacial deposits. And for engineering data needs, I would like landing site confirmation, so sort of a blanket over that LZ crater just to make sure we can land in there safely. And also to look at traverse capabilities and rock abundance. And I said this earlier, I think it's a good idea to have small rovers on the surface, maybe not even MSL size, but just a big remote control car with sort of the ability to get rocks and maybe even a ChemCam sort of instrument to do reconnaissance. And you don't have unlimited EVAs, and so in the times that the astronauts are going to be stuck inside, this is a way to get them outside and still keep exploring and keep their morale up a little bit. And if you do extend the EZ, you can, here's the 200-kilometer radius, and it doesn't really expand much into any other units, but you do get a lot more of the same units, unlike the other site that I was proposing. So more Noachian Highlands, you can actually get to the edge of these outflow channels and all the way almost to the other rim of Moreau crater. And that's it.
If we could have the other two speakers come back down, please.
Don't think they're quite ready, or are they? Are you breaking now? Okay.
So open it up. Any questions from the audience? Oh, come in so you can be seen. Here you go. Why shouldn't you be blinded too? Yep, question at the back. In the blue. Just remember to say who you are, what you are, etc. Where you're from. It's coming, it's coming. They're everywhere.
Excellent. Stereo. My name is Paul from Michigan Tech, Van Susante, if you want to know. The question I have is, you were talking about the ice that was just on the surface, basically, and you said the dissipation rate was consistent with what you would expect there. Could you elaborate a little bit on that? I'm kind of curious how long ice is stable under those conditions.
Okay, so I didn't do those measurements myself, but we have kind of subsequent high-res images. So when we see a new impact take place, you get the follow-up image as quickly as you can. Like, this ice is going to disappear over time. I don't remember the exact time scales, but if you get it soon enough, you can see the ice, and then if you keep taking repeat images, kind of each one, it subsequently fades over time, but I don't remember the rate.
The one I pulled off, the high-rise one, was a year between the two images.
A couple of comments. First, regarding the Arcadia sites, I think several people asked for more radar data. I suggest you look at the existing radar data first and then see if you need more. In particular, there's a recently published study that I was involved with. Allie Bramson was the lead author, down the hall, I think. Donna, and there, at least some of the questions that you still had on your slides could be addressed, or at least there are some constraints on how thick the ice-rich layer is, which is tens of meters, we believe, and
which is assuming it's the same ice layer, which it most likely is,
right.
but there could be multiple episodes.
Right, and also some constraints on the possibly the mixing ratio, because this ice does not look like it's quite as clean, at least through all the tens of meters thickness. Also, regarding the Proto-Nihilus site, again, more radar data is always better, but the radar data that we have there doesn't seem to penetrate through the lobate debris aprons and the other, in the morphology and CTX, it looks like the same stuff, but it's kind of a mystery that we're still trying to puzzle out why we don't see through the stuff in that region.
Okay, good to keep in mind.
Rob Mueller, NASA Kennedy Space Center. We're developing mining and excavation implements in my lab, and the strength of the water ice is dependent on the temperature, how dirty it is, various other factors. So I think a few of you made statements like you just dig it up, and that's great to hear. So I'd like to know how you just dig it up.
That's your job.
And I can do that, but I need the properties of the material, and so I need to know how dirty it is and how cold it is, and then I can give you a strength. But so is that available, that data?
Yeah.
I mean, more data is always better, right? That's the theme of this.
But it's a fair point. I mean, has anything been done in Earth labs with analog materials, or is this just a modeling result that you'll be basing your thoughts on? And I think it's one of the things we'll discuss tomorrow is the issue with resources going forward and how we get answers to those questions.
I lost the mic, but yes,
I think a
So
lot
you
of
know the answer, so why are you asking us?
I think a lot of the people have said that they can dig it up, and I think they're more referring to that they can access it by moving the top meter or so of material away from it. Then what do you do with it? That's another question. One of the older techniques I saw, going way back, you can actually tent an exposed ice region, leaving it at standard atmospheric pressure. And if you had a dark material, you actually raise the temperature inside that a little bit, and then you can use the normal sublimation process and cold trap the material. So there are some interesting things that have already. There's a lot of stuff that's out there that's been done, that's been thought about before. So
There was another question. You pointed. No. Really? No more? Oh.
If we have more time, let me ask a longer question. We've heard a lot of discussion about resource utilization, but let me turn the question back to astrobiology. What is it about these sites that would benefit from putting a human there to explore for astrobiology? How exactly do you envision that happening? And rather than putting too much pressure on these three, I need some help from people in the audience. I know Pan has put some serious thought into this, but I'd like to hear from you three, and then we'll throw it out to the rest of the group.
Well, I would say, first of all, it might depend on what your planetary protection regulations are in the first place. If we're going to be melting the ice, there might be subsignatures in that, but it's whether you can actually use that.
I think the argument's the same for any of the science that we're not doing robotically. The human in the loop, puts another, the set of eyes in the field where you can react to stuff quickly, I think is the key there. I don't know if the biological versus the geological versus, any other type of study is really that much different. It's just the focus on what you're looking at. I think that would be the main one.
So what I'm thinking is if you have an astrobiologist on the surface of Mars, they're going to be doing astrobiology work, whereas now you have a whole team of people with multiple interests doing lots of stuff with robots. And so you have a person up there dedicated to doing one thing, and they're going to be interested in that. And it might make doing the work a little easier and more specialized.
So you just want to give Paulie Lane a chance on the phone. Do you have anything you want to add for any of the questions? Because it's not really very easy for you to sort of just butt in.
Not much.
No, it's okay.
Humans are more versatile than robotic exploration, and there has been a lot of field testing of astrobiologists doing simulated Mars environments to practice this kind of task. So it would be a benefit for astrobiologists to be in situ. So that's my comment.
Pan, may we call on you to share some of your vision of what a human crew could do in the area of astrobiology, or how they might go about it?
I'll take this one. So this is a great demonstration of why we need this meeting. Astrobiology is not a monolithic discipline. I'm an astrobiologist, but my training is in mineral physics, and now I measure the noble gases in the Martian atmosphere. So from that perspective, I'm just one of a bazillion people who study a lot of things on the Martian surface. So the reason why astrobiologists want to be on the surface with a team is, first of all, we want to be on the surface with a team because it's an interdisciplinary science. And I think Jim Head said it best today in the session when he started talking in the first half of his talk about the whole planet perspective, and how if we really want to learn the planet, we have to be able to live off the planet. So in that regard, astrobiologists are a microcosm for the full span of interdisciplinarity that the team is going to bring. And that also extends to ISRU, not just for the resources that you need for staying alive and for industrial applications, but to understand the exploitable resources that are necessary for actually doing science and then conducting the science of exploitable resource acquisition. So from the perspective of having heard a bunch of these talks today and hearing yours, I think the question that we should be asking ourselves, not just for astrobiology, but for all of Mars science, is, if we want to get a handle on the entire planet, which amongst these sites best sets the stage to teach us things about the whole planet as well as the science of that specific site? And what do we need to expand from whatever site we go to so that we can start putting together our cell phone network and our power distribution?
And all that in a 5-hour workday.
Any other questions? Okay. Oh, yeah.
I just had a comment along those same lines, just to say that I think some of our approach to this has been, wow, look at how much more we can do because we have a 100-kilometer radius rather than a much smaller radius from Mars 2020. But the real leap here is from a robot that takes a very long time to do each thing to a human team which moves very quickly, and humans being optimized for taking in huge amounts of data, analyzing it, and prioritizing it. And so being able to do an amazing amount of science that we haven't been able to do, or that has just been stretched out over a really long period of time. And so I think that putting that in our minds, not only how much we can do because we can reach out farther, but how much we can do. I mean, a lot of people have been studying this, just what huge advantages it brings to Mars, not just disadvantages that we have to keep ourselves alive, but huge advantages to the science that we can discover going around as human beings on the surface.
And I think Jim put it well. at least this morning when he was talking. We got to think of this as the long term. It's not a flags and footsteps type of thing if we do it right, in my opinion. I believe his too. So that kind of also changed the perspective on science. And I kind of quipped there with the 5 hour workday. We had one of our crew members talk about that. But it's going to take a lot of work days to start building the fundamental science that we see here on Earth that we've been doing for thousands of years. So, if that makes sense.
Okay, well, thank you again. So we'll break now till 3:50. Before you run off, just one other thing to keep you informed. So we'll be finishing a little before 5, and then we have a reception at 6:15, and a poster session then too. But in between, we have 2 talks for you. One from Jim Green, the Planetary Subdivision, Planetary Sciences Subdivision, and then also Jim Watson, the Mars Exploration Program Director. So they'll both be giving talks in between finishing. So don't just run away at the end of the next session. We'll see you in 15 minutes.